with protein misfolding. What are the mitochondria? The mitochondria are the powerhouse in the cell. They create energy, and the energy they produce is ATP, and that's what the body runs on. They help with the immune system. Again, calcium, you're going to see calcium all over the place. Calcium homeostasis and apoptosis, which is programmed cell death. This is a way the body cleans up after itself. Mitochondria are even related to stem cell regulation. And then, of course, we do have mitochondrial DNA, and that's the maternal DNA that's passed down through the female line. So here we have the mitochondria that's producing ATP. This is with oxygen. What damages mitochondria? A bunch of drugs damage mitochondria. Alcohol damages mitochondria, over-the-counter pain medication. And of course, they can also be damaged by the apolipoprotein E4. And that's the one we'll talk about next week. Is related to Alzheimer's. So if we have problems with the mitochondria, like uncoupling, then the problem will be that it's unable to make ATP. So it can't make energy. That's a problem. We need, I guess I can't move that. Oops. We need that mitochondria to be making energy. It's the free radicals and the oxidative stress that cause the uncoupling of the mitochondria. Remember that free radicals, that's an unstable molecule, be an atom, or a molecule. It's that it's missing an electron. The body doesn't like uneven numbers of electrons. It wants to have an even number. And so then it's like, let me get another electron. I need an even number, and it's looking for it. If you don't have an antioxidant, then it's like, I'm going to grab it from here, and then that's going to cause other problems. So oxidative stress is when free radical steals an electron from another atom in the presence of oxygen. That's all it means. It just is not good. So another problem with the mitochondria is that if it can't block the NMDA receptor, then inflammation is created. So the uncoupled mitochondria can't block it. The coupled mitochondria can block it. And if the NMDA receptor is unblocked, then again, here's calcium. Calcium is highly inflammatory. And when the calcium rushes in, it's supposed to be counterposed by magnesium, but without the mitochondria there, it's not counterposed. And so then we get neuronal death, and that leads to inflammation. Remember that the NMDA receptor is a glutamate receptor. Glutamate is excitatory. It's an excitatory neurotransmitter. And so you're getting this excitatory neurotransmitter that doesn't have a place to rest. And so it's also like it's seeking, in a seeking mode. The third problem with mitochondria is that when you have the destruction of the mitochondria, because there's no energy in the neuron is going to die. And so that's not good. You need your neuron. So we talked about neurodegeneration being a combination of mitochondrial dysfunction and protein misfolding. Now we're going to talk about protein misfolding. So proteins are made out of amino acids. Amino acids are the building blocks of proteins. Everybody takes amino acids in their smoothie, something like that. Amino acids are like a chain, and then they kind of hook up, and then they kind of fold up, and then they kind of bunch up, and that's what is a protein. Protein is a bunch of different amino acids combined. So they have to fold in a certain way in order to be able to receive things and transport them or do the job that they're designed to do. They need to be folded in a certain way. If the protein is misfolded, then you're going to end up with disease. So like Alzheimer's disease has the misfolding of the amyloid beta and the tau protein. And that's what we're going to be kind of focusing on for this. So this is the amyloid beta plaque. Amyloid beta plaque is made out of a bunch of different misfolded amyloid beta proteins. And then the tau neurofibrillary tangles is also made out of misfolded proteins. We're going to talk about amyloid beta plaques first. These amyloid beta, the protein, is produced by astrocytes in the brain, neurons, skin, skeletal muscles, intestinal epithelium, the cells that line the intestine, and even bacteria. Bacteria produce amyloid beta as a biofilm. I didn't know that. And it has a normal function. Normal function is to protect from infections. It's as good as drugs for antimicrobial effects against 11 different identified microbes. It suppresses tumor growth. It can repair the blood-brain barrier. It promotes recovery from brain injury, hypoxia, and even autoimmune disease. It regulates the glutamatergic and the cholinergic synaptic function. So remember how we were just talking about the NMDA receptor and how that's glutamatergic? Everything is going to start fitting together. It also contributes to memory consolidation. It's a great protein, amyloid beta. So what's supposed to happen? It's supposed to do its job. And then you're supposed to poop and pee it out or sweat it out. Sounds pretty good. But if it forms plaques instead, then what's going to happen is, again, the protein is going to be disrupted. We're not going to have, the calcium. We're not going to have homeostasis anymore. That leads to inflammation, dysregulation of energy and glucose metabolism, mitochondrial oxidative stress leading to death, and then neuronal apoptosis, which also is death. Amyloid plaques do. But what causes them? This is a dominant model. What causes them to form? So there's something that's called the amyloid precursor protein, APP, amyloid precursor protein. It's a normal protein. It crosses the nerve cell membrane. That's what it's supposed to do. And it's supposed to be pruned by this enzyme called alpha secretase. Top part cut by alpha secretase, bottom part cut by gamma secretase. And no plaques form when it's done properly. It should be a peptide chain that's 38 peptides long. The body's like, awesome, I know what to do with that. Send it off to do its job. But sometimes what'll happen is that instead of alpha secretase doing the cutting, you'll get beta coming in. Beta secretase will come in. And sometimes there's even a mutated gamma secretase. When they prune the APP, you start getting these long strands. It can go up to 48. And then the body's like, wait, this is like really like long. It's getting kind of tangled. And then what happens is that it interacts with that apolipoprotein E. And if there's inflammation present, then it will start getting tangled on itself and forming these plaques. So you can see here, APP, amyloid precursor protein, is a glycoprotein. That means sugar plus protein. And here we have the alpha secretase. That's cutting it. It's supposed to cut it right there. Great, cut it beautiful. Here's the gamma secretase. Cut it beautiful. Non-amyloidogenic pathway. That means you don't get the amyloid plaques, right? This is normal. Then it can do its job. Uh-oh. Here we go. Now this time we're getting beta secretase coming in. Oh dear. It gives it a cut. Still got the gamma secretase, and we got the amyloidogenic pathway because we got the long peptide chain. The body's like, does not compute. Not awesome. I don't know what to deal with that. Too long. So why? Why does this APP, amyloid precursor protein, not function properly. Beta secretase, we talked about that. It gets activated. We'll talk about later why it's activated, or there could be mutation of gamma. That's minor, more minor than the beta primary. Low estrogen, that plays into it. Alzheimer's is more common in women who are postmenopausal. Men have low estrogen also, but their receptors are not used to having higher estrogen. And improper exposure to metals. That's another reason that you can have improper function of the amyloid precursor protein. So this estrogen. So estrogen binds to the receptor and activates the alpha secretase. If you don't have as much estrogen as you're used to having, then you're going to have impairment of cleaving this amyloid precursor protein. And what we also know in mice, at least, is that estrogen downregulates beta. So it's kind of like a double whammy. If you have low estrogen, then you're not going to get activation of the alpha, and then you will be more likely to get activation of the beta secretase. And then the metal exposure, we know that the amyloid precursor protein responds to iron, copper, zinc, and that they need to be in the right ratios in order for it to function right. So that's a component. We also know that copper is found in the amyloid plaques. And of course, excess copper will cause death of the synapse and the neurons. Of interest is that when you get this long string of peptides, the long amyloid beta string, what happens is that it turns on or induces the hyperphosphorylation of tau. And that is the thing that causes the tangles. And why is hyperphosphorylation turned on? It's a normal part of development, and the enzyme that breaks it down, phosphorylase, is decreased with hibernation and hypothermia. So phosphorylation is important for cell growth and renewal. And so when you need that, you will have more of it. So here's the healthy microtubule right here. That's stabilized with the tau protein. That's part of the neuron axon. And then with the amyloid beta influence, then what happens is that you start getting breakdown of this microtubule and tangling up. And the tau is really important. It's supposed to, it's what stabilizes that tubule so that it can carry nutrients that keep the brain healthy. It's helpful for cell signaling, for synapse plasticity, so responsivity to the environment, and for the genomic expression. So it has a lot of different functions. And when it malfunctions, then it's just like a clump. It doesn't work anymore. It can't help the tubule stay open, can't carry nutrients, and then everything falls apart. So we're talking about misfolding of proteins. We're talking about problems when proteins misfold. So that's one of the things, right? Protein misfolding in itself is a problem because the form of the protein is changed, so it can't do its job. And so we talked about amyloid beta and we talked about tau and how they are compromised in the ability to do their job when the folding is wrong. Other things that you probably are familiar with is like hemoglobin. That's supposed to carry oxygen. If hemoglobin is misfolded, like say sickle cell anemia, right? It can't carry the oxygen. So sickle cell anemia is awesome for preventing malaria. but not awesome for carrying oxygen. And so there's like this trade-off that's happened with sickle cell anemia, for instance. And if a mitochondria protein is misfolded, like we were talking about, you can't make ATP, so you don't have energy. So you can't like renew. You can't have energy. You can't continue living, basically. So that's one of the problems. We talked about misfolding of protein itself. The other problem with misfolded proteins is if they don't get cleaned up properly. So if you have a misfolded protein, at least it should get cleaned up, and then it'll be less of a problem. But if it doesn't get cleaned up, you have two problems on your hands. So the misfolding of proteins itself is caused by advanced glycation end products. That means a sugar and a protein combine, or a sugar and a fat combine. What do you get? You get trouble. So the thing that everybody knows about the most is like brown spots. Like I have a lot on my hand. These are all advanced glycation end products. This is all a product of sugar and protein, or sugar and fat combining incorrectly in a way that's harmful. So everybody knows about hemoglobin A1C. Hemoglobin A1C is something that we use to measure more or less how your blood sugar was over the past 3 months. But it's actually also measuring inflammation in your system, because it too is representative of being an advanced glycation end product. We talked about free radicals. When there's an uneven number of electrons in a molecule or an atom, that can cause misfolding of proteins. We talked about reactive oxygen species, which is a free radical in an oxygen environment that can cause misfolding of proteins. So the misfolding of proteins caused by the advanced glycation end products is a glycotoxin. That's bad. And if it combines with protein, you're going to get inflammation, you're going to get antibodies, blood vessel damage. It can be related to type 2 diabetes and type 1 diabetes. And it's when its receptor is involved, then you're going to get inflammation there in the receptor. And it can also produce its own free radicals. And then that goes on to just wreak havoc everywhere, even in the DNA and the cell membrane. So it's not awesome. So this is a picture of a free radical. So you can see it's like, I need an electron. Give me an electron. Best place to get it is with an antioxidant. So that's why you need to eat a lot of fruits and vegetables, right? Because they're super high in antioxidants, for instance. So stealing an electron from an antioxidant is the best thing that a free radical can do. That's the best place to get it. Now, here's the reactive oxygen species. These are free radicals in the presence of oxygen. And they're also like the hydrogen peroxide is one that you'll see in all of the like pathways that's thrown off a lot. And that's a poison. That's a poison. So what's supposed to happen to these misfolded proteins? They're supposed to be degraded. There's different pathways. They can be degraded along. The ubiquitin and the autophagy pathways are the ones that they're degraded on. So here's the ubiquitin one. So what impacts this pathway are things like epigenetics, metabolism. These things can inhibit the ubiquitin pathway if they're not done properly. And so what we need to do is to optimize the epigenetics, optimize our exposure, optimize our metabolism, optimize our stress level and how it's expressed in the endothelium or the this is what we're shooting for. So then when we talk about autophagy, we're talking about, part of it is the chaperones. So you can see there's chaperone mediated autophagy here. That's what we're going to talk about next. This is chaperones. I don't like that name. I think they should be called nannies, because they're not just like a chaperone. Let's say a chaperone is like your little brother or sister being sent on a date with you, so no funny business happens. That's a chaperone, right? Nannies do a lot more than that. And so these chaperones are more like nannies. They're controlling the quality of the protein, because what they do is they oversee the folding of proteins. Like a nanny, let's say the nanny is helping you clean your room. The nanny will be like, okay, this is how you fold your shirt. Now you give it a try. So make sure that you fold your shirt the right way. And then the nanny would be like, pretty close. Let me show you again. And then would fold it correctly. That's a nanny does that. Chaperone doesn't do that. That's the way I'm thinking about it. And then after the nanny oversees cleaning the room, then the nanny will be like, okay, now let's take all the dirty clothes out. That's kind of chaperoning piece of it. But also that's what a nanny does. So that's a normal part of cleaning up misfolded proteins. So one of the chaperones, I call them nannies, is a heat shock protein. These are awesome heat shock proteins. They help fold new proteins. They help prevent the proteins from sticking together. They are good at breaking down misfolded proteins. They transport the proteins, and what's really special about them is that really good at finding the beta amyloid plaque. When they find the beta amyloid plaque, they're like 911. They attach to it, and then the glial cells are able to like see it. They're able to identify it and then attack it themselves. These are the glial cells. Glial cells are in the brain. So we talked about the microglia before. The astrocytes are glial cells that are for the blood vessels, and the oligodendrites are the glial cells that are for the myelin part of the neuron. Those are the glial cells. And so the microglia, they're supposed to help clean up inflammation. So if there's trauma, if there's infection, anything that creates inflammation, they'll be like, let me handle this. And so there's a few different kinds of microglia. And what happens with initial exposure of a pathogen or a tumor or something like that is that there's a pro-inflammatory response. This is normal because they're trying to kill it. So that's normal. So that should be turned on and turned off. And then also we have the M2 or microglia number 2, which is an anti-inflammatory microglia. This is the one that promotes tissue remodeling, repair, angiogenesis. And so with acute disease, this anti-inflammatory M2 microglia is neuroprotective. That's awesome. But what happens is that with chronic exposures, chronic disease, the brain gets switched over into this neurotoxic M1 dominance, which is pro-inflammatory. And so like the cells that are supposed to be cleaning up the mess actually become part of the mess. And so that's why we want to intervene as soon as possible. We don't want to let things, spiral out of control, because the body becomes dysregulated in its pro and anti-inflammatory systems. And so here's an example of Alzheimer's. So this is your microglia, it's resting like tra-la-la. And then we have early Alzheimer's. And what's supposed to happen is that most of that amyloid beta is going to be cleaned up, discarded, pooped and peed, sweated out. Some of it might not be, and then that's going to be shifted up into a more chronic state. The microglia then in the advanced or chronic Alzheimer's disease, we have the activated microglia. And then we're getting, remember those RAGE, the receptor for the advanced glycosylated end products? Ooh, those are here. We have inflammation already. Ooh, this is the beta secretase. Ooh, that's coming on. Oh, and now we're getting all these pro-inflammatory cytokines going on. And now we've got the amyloid beta accumulation and neuronal damage. So that's what happens when we have chronic activation of microglia. They become pro-inflammatory. So again, these heat shock proteins, that's where we started at. They're the chaperones. They're the ones that help us clean up things, help to identify the beta amyloid plaques so that the glial cells can attack it, try to clean it up. They're super awesome and important. And so we need to upregulate them. So the main way that they're upregulated is they're called heat shock proteins. It's through heat. So taking a sauna is really awesome. Trying to sweat every day, if you can, is awesome. A lot of people have a problem sweating. It's hard for their body to sweat. And so if you can get in the habit of sweating, this is awesome. Definitely do not use antiperspirant because you need to sweat. So it's funny though, because these heat shock factors that activate the heat shock proteins are not only hypothermia. Look here. There's hypothermia, hyperthermia, too much heat, sauna. It's also hypothermia. So that's like cryotherapy. So now cryotherapy is like a thing for chronic disease. You have to go into like this really super cold place because that's another way that the heat shock proteins get turned on. This is a combination of ischemia and reperfusion. And so nowadays there's a kind of therapy where you tie this kind of like a rubber band around an area of your body to create ischemia, which is where there's no blood flow, right? And then you release it, and then there's hyperperfusion. And so that's another way to turn on the heat shock proteins. In manual therapy, we use our hand to do something that's called a blood stop, where you would use your hand to press down on a vessel, create a blood stop, and then release it suddenly so that you can get that hyperperfusion, turning on the heat shock proteins. And it's funny, right? Because both, again, hypoxia and hyperoxia, so not enough oxygen, too much oxygen, can also turn on the heat shock proteins. So they can be like the Wim Hof breathing, for instance, the oxygen tanks, for instance, the highly pressurized oxygen, and energy depletion turns it off. So basically, when the body's in a extreme state, this is going to turn on the heat shock protein. So this would be fasting. Acidosis, this would be like ketosis, because you put you in a pH that's acidotic. Viral infection, the body's like, got to get to work here, turn on the heat shock proteins. The reactive oxygen and nitrogen species will do it too. So one of the main reasons that misfolded proteins are not cleaned up is because the insulin degrading enzyme is used both to clean up the amyloid beta plaque and insulin. So if there's too much insulin circulating in the brain, the insulin degrading enzyme is going to be like, I'm going to be working on that insulin instead of the amyloid beta plaques, because working on the insulin, degrading the insulin is my number one priority. Insulin is highly inflammatory. You think glucose, you think sugar is inflammatory. Insulin is also inflammatory. So the body's like, I don't want that inflammation. I'm going to degrade that. And then I'll work on the amyloid beta plaques when I have time. So we have this shift away from addressing the amyloid beta plaques to addressing the insulin by the insulin degrading enzyme. So when we think about insulin, we think, oh, you know, that's like that. That's what escorts the sugar into the cell. So you actually have energy. It creates the glucose homeostasis. But insulin does a lot more than that. Insulin and the receptors in the brain are also important for neuronal integrity. They help us think, cogitate. They help with the neurotransmitters. And again, we have the NMDA receptors that are for energy, for balance, and anti-inflammatory when done right. The insulin receptors are important for maintaining the excitatory synapses. So that's the glutamate, that's the acetylcholine. They help with the insulin receptors help with the dendritic spine formation, and also, again, the apoptotic pathway. So breaking down, taking away of cellular debris. So this is the reason that Alzheimer's is called type 3 diabetes. Because a lot of people who have Alzheimer's have diabetes of the brain. They have too much sugar in their brain, too much insulin in their brain. So the insulin degrading enzyme cannot work on the amyloid beta plaques. They're working on the insulin. So what you see with Alzheimer's is progressive insulin resistance in the brain. This leads to neurotoxicity, neuronal stress, neuronal degeneration. Because you have too much insulin, you're not getting the amyloid beta plaques cleaned up, and and you're also getting impaired insulin signaling. So it's a problem upon a problem upon a problem. Too much insulin makes amyloid beta accumulation inside of the neurons. And then you have that breakdown into tau, and it's this slippery slope. Everything is falling apart. It's becoming very sticky, very inflamed. So amyloidosis, or the amyloid beta plaques, are not the cause of Alzheimer's. And that's why all the research has failed. That's why the drugs fail, because it's not the cause, but it's a mechanism of pathology. Something else is driving it. And that thing that's driving the amyloidosis is the thing that we should be looking at, not the amyloidosis itself. So Alzheimer's is a synaptic failure that is caused by the amyloid beta plaques and the tau hyperphosphorylation. But something is driving that. And that is what we need to look at. That's what we need to find. And that's what we need to address. And that's what this program is about. And so even though, we know a lot of things like the shrinking of the hippocampus, we know there's a new protein that they've discovered that's related to Alzheimer's disease. It's not the cause. It's related. We'll find out more about it with time. We know that the mechanisms have to do with misfolding, mitochondrial dysfunction. Those are not the cause. That's part of the problem. It's not the cause. And the problem is with all the research is that we're not looking at the right thing as the etiology, as what's turning on this process. And we want to change that. So for Alzheimer's, there's a progression where you're losing smell, you're losing your ability to identify flavors, you're losing your episodic memory, which is the hippocampal memory, you're losing cognition, there's emotional changes that happen, aggression, losing the ability to speak and communicate properly, find yourself in time, day, night, all of that, confusion, leaving, getting lost, not knowing where you are. Is it day? Is it night? I don't know. And then losing your ability to move properly and swallow and to recognize loved ones. And this is the progression that breaks your heart, that we want to avoid. We want to step in here. We want to step in here when we first start noticing, oh, something's happened in here. We want to address that. That's what this program is about. Biomedicine, want everything's normal until you can't recall somebody's name. That's too late. So our three phenotypes: inflammatory, the predominant one; atrophic, not enough nutrition; toxic, something's there that's agitating, that the body's fighting against or trying to seal off. We have to get rid of. We talked about the methylation. We need to be able to methylate properly in order for everything to heal. We have to be able to produce and transmit neurotransmitters. We have to have a well-functioning immune system, vascular system that has proper flow. We have to be able to produce and use energy and have a strong barrier